Welcome to another edition of Math for No Reason. In this edition, we will prove this result. So let S be a set and Ps be the power set of S. That means the set of all subsets of S, including the null set. And we define the symmetric difference delta in this particular manner. So delta is a binary operation, and A delta B is A minus B union B minus A, which is equal to A intersection B complement union B intersection A complement. We have to show that the power set of S with the binary operation being the symmetric difference is an abelian group. Now what we have to show here? We have to show several properties. The first one is closure. That means if we take two sets A and B, A delta B is again a set which is included in the power set of S, and which is of course trivially true, so we don't need to bother about that. The second one is the existence of an identity. So we will have to find an element from the power set of S such that A symmetric difference with that element will give back the same element. That we have to find an element, say X, such that A symmetric difference X is equal to A for all A, and that is also equal to X symmetric difference A. The third property is that of the existence of an inverse for every element. By that we mean that for any element A, we have to find an element Y such that A delta Y is equal to X is equal to Y delta A. The fourth property that we will prove is commutative. That means that if you are looking at A delta B, that is equal to B delta A, and of course associative, that is A delta B delta C is equal to A delta B delta C. If we can show all these five properties, then we can claim that the power set on S with the binary operation delta is an abelian group. So we will take one by one. So the first one that we have already seen is the closure, because A delta B is another subset of S, so the closure is true. The second one that we want to look at is the commutative property. Now if we look at this expression of A delta B, you see that it is A intersection B complement union B intersection A complement. If you look at B delta A, then this would be B intersection A complement union A intersection B complement, and that is exactly what we need for commutativity. So commutative is also true. A delta B is equal to B delta A. Now commutativity will help us in proving 2 and 3, which is the existence of an identity and existence of inverse. So let us first look at identity. So if you look at A delta phi, what you get? You get A intersection phi complement union phi intersection A complement. A intersection phi complement is the universal set, which is in this case S, and phi intersection any set is phi. So union phi, so that remains as it is, and A intersection S, A being a subset of S, is A. So A delta phi is equal to A, and by the commutativity we know that this would be equal to phi delta A. So therefore the set phi is the identity element. Okay, so we can replace this X with phi, and we claim that this phi is the identity element of this binary operation delta. So phi, or the null set, is the identity element with respect to the symmetric difference operation on the power set of S. Now once we have done that, let's come to the inverse. Now again observe that A delta A is A intersection A complement union A intersection A complement, which is in both cases null. So this is A intersection A complement is null, union again A intersection A complement is null. So you get the null set, and the null set is the identity on this power set of S. So therefore, we see that every element A is its own inverse, and therefore we can claim that every element has an inverse which is itself. So what is left is to prove associativity. So indicator of A delta B is the indicator of A intersection B complement plus the indicator of B intersection A complement minus the indicator of A intersection B complement into the indicator of B intersection A complement. And breaking it further, we have IA into IB complement plus IB into IA complement minus IA into IB complement into IB into IA complement. And IB complement is 1 minus IB. So IA into 1 minus IB plus IB into 1 minus IA minus IA IB into 1 minus IA into 1 minus IA. So simplifying. So here we have used the fact that if you multiply IA with IAIB, we get back IAIB, because IA takes values only 0 and 1, and similarly for the next, and the same for the last term also. So this is the result that we will need, that the indicator function of asymmetric difference B is IA plus IB minus twice IAIB. So when we look at I of A delta B delta C, we will have A delta B plus I of C minus 2 IA delta B into I of C. So simple algebra tells us that I of A delta B delta C is IA plus IB plus IC minus twice IA into IB minus twice IA into IC minus twice IB into IC plus 4 times IA into IB into IC. We will now find out I of A delta B delta C, and we will try to check whether it matches with this expression. So I of A delta B delta C after simplification turns out to be IA plus IB plus IC minus twice IAIB minus twice IAIC minus twice IBIC plus 4 IAIBIC, which is the same expression that we have got here. So therefore, we can claim that these two indicator functions are same, and if two indicator functions are same, then the sets of which these are indicator functions are equal. So therefore, this means that A delta B delta C is equal to A delta B delta C. So we have proved that delta is associative. So since PS delta meets all the conditions of an abelian group, so therefore we can say that PS delta is an abelian group. Thank you.